This is the first time we have been begin to explore this new region of space, interstellar space.
Tremendously exciting to think that a spacecraft I had worked on, I had been a part of, was actually now leaving our solar system.
In the late summer of 1977, a slender, gold-trimmed spacecraft sat on the launch pad at Cape Canaveral. Its purpose was as ambitious as anything humanity had ever attempted. This was Voyager 1, a machine barely taller than a small car, yet destined to leave the solar system entirely, carrying with it a record of our existence. NASA's vision for this craft was simple in statement: travel to the outer planets, study them in unprecedented detail, and keep going for as long as the hardware would allow. But this was more than simple explorations of distant worlds, because while the original goals were bold enough, what Voyager 1 would eventually encounter went far beyond anything its designers had ever imagined. Voyager 1's onboard memory, just 69 kilobytes, was smaller than the size of a single email today. Data was stored on a magnetic tape recorder, the same kind of technology once used in 8-track audio cartridges. Every component was chosen for durability, redundancy, and the ability to function without human hands for decades. Its most visible feature was a 12-foot wide high-gain antenna, a white dish that served as its lifeline to Earth. Through this, it spoke to the Deep Space Network, a series of giant radio dishes stationed around the globe. Even at launch, a single message took hours to travel the distance between Earth and the spacecraft. It relied on hydrazine thrusters for subtle changes in its orientation, keeping the antenna locked onto Earth. Its power came from 3 radioisotope thermoelectric generators, RTGs, that converted the heat from decaying plutonium-238 into electricity. The generator contained a specially produced form of plutonium dioxide. The natural decay of this radioisotope gives off heat, which these thermocouples can turn into electricity. At launch, they produced enough to run all the spacecraft's systems comfortably. But every year the power output dropped, and now it has less than 23 watts left, barely enough to light a dim bulb. The instrument suite was designed to observe almost everything it passed: ultraviolet and plasma spectrometers to study atmospheres and charged particles, cosmic ray detectors to measure radiation from distant stars, a magnetometer on a long boom to keep it away from interference, and, of course, its cameras, capable of capturing planetary surfaces in vivid detail. It was, by modern standards, a primitive machine, but it was also a masterpiece of engineering, the kind of craft that could keep going long after its creators stopped speaking about it in the present tense. And in time, it would face challenges no one could have prepared for. More than a decade before Voyager ever left the ground, a quiet discovery changed the scale of its mission entirely. In 1965, NASA engineer Gary Flandreau, working at the Jet Propulsion Laboratory, was studying the movement of the outer planets when he noticed something rare, an arrangement of Jupiter, Saturn, Uranus, and Neptune that happened only once every 176 years. It was a cosmic alignment that offered a kind of shortcut through the solar system, a path where the gravity of each giant planet could sling a spacecraft toward the next without using more fuel. In ordinary circumstances, reaching Neptune from Earth would take 3 decades of steady travel. But using this gravity assist technique, the journey could be cut to just 12 years. The spacecraft would essentially fall toward Jupiter, gain speed as it swung past, and then repeat the process at Saturn, Uranus, and finally Neptune, each planet handing it off to the next in a chain of momentum. This was no small adjustment. To the mission plan, it reshaped everything. The launch window would be tight, just a few months in the late 1970s, and missing it would mean waiting another lifetime for the same chance. It also meant building not 1 but 2 spacecraft, ensuring that the opportunity was used to its fullest. Voyager 1 would focus on Jupiter and Saturn, while Voyager 2 would take the longer, more ambitious path to Uranus and Neptune. The alignment was a gift that couldn't be ignored, and it set the stage for a mission unlike anything attempted before. What lay along that path, however, was more than just planets. There were discoveries waiting that would rewrite our understanding of the solar system itself. Voyager 1's first great leap beyond Earth's neighborhood came in 1979, when it approached Jupiter. The giant world was more than just a swirling ball of storms. Its system of moons turned out to be a miniature solar system of its own. Voyager's cameras revealed volcanic eruptions blasting from Io's surface, the first active volcanoes ever seen beyond Earth. On Europa, smooth icy plains hinted at a hidden ocean beneath, a tantalizing possibility that life could exist far from the warmth of the sun. The spacecraft also captured the planet's faint ring system, something no one had known existed before. Just 2 years later, Voyager 1 reached Saturn, and the surprises continued. The rings were not solid bands, but intricate braided structures of countless ice particles shaped by the gravitational pull of tiny shepherd moons. Titan, Saturn's largest moon, was cloaked in a thick orange haze, an atmosphere denser than Earth's, rich in organic molecules that raised questions about what might be happening on its surface. The images and data transformed Saturn from a distant, mysterious ornament in the night sky into a complex and dynamic world. Voyager 2, on its extended path, would go on to reveal Uranus tipped sideways on its axis and Neptune with supersonic winds howling across its dark blue atmosphere. Together, the Voyagers expanded humanity's understanding of the outer planets in ways no telescope could match. By the time the planetary encounters ended, the mission had already delivered more than anyone expected. But as the spacecraft moved, beyond Neptune's orbit, a new frontier began to unfold, one that would take them to the very edge of the sun's influence, and what waited there was unlike anything the mission planners had predicted. Beyond the orbit of Neptune was a vast and turbulent boundary, the heliosphere, a bubble of charged particles and magnetic fields created by the sun. Inside it, the solar wind dominates space. Beyond it, the influence of other stars begins. For decades, scientists wondered where this invisible edge, called the heliopause, truly was. Voyager 1 was destined to find out. As the spacecraft pushed deeper into the outer dark, its instruments recorded a steady drop in the number of charged particles from the sun, while cosmic rays from interstellar space began to rise. These gradual changes hinted that the edge was near, but pinpointing it would take years of patient monitoring. Then, in August 2012, the data shifted dramatically. The solar wind's pressure faded almost entirely, replaced by a denser, cooler plasma that could only come from beyond the sun's reach. Voyager 1 had crossed the heliopause, becoming the first human-made object to enter interstellar space. The achievement was more than symbolic. It gave scientists their first direct measurements of the interstellar medium, the thin, ghostly material between the stars, and confirmed theories that had only been modeled from afar. When Voyager 2 made its own crossing in 2018, it confirmed the pattern, showing that the heliopause was not a perfectly smooth shell, but a shifting, irregular boundary. Now both spacecraft were traveling through a realm untouched by anything from Earth, their signals carrying the story of a journey farther than any before them. And along with the science, Voyager carried something else into this uncharted territory. A message meant for any intelligence that might one day find it. Strapped to the side of Voyager 1 was something that had nothing to do with measuring plasma waves or magnetic fields. It was a time capsule, a gold-plated copper disc, known simply as the Golden Record. Designed under the guidance of Carl Sagan and a small team, it carried 115 images and a collection of sounds from Earth, greetings in 55 languages, music from cultures around the world, the sound of rain, ocean waves, and a mother's heartbeat. Its purpose was not to send instructions or blueprints, but an introduction, a portrait of what it meant to be human in the late 20th century. The cover of the record bore diagrams showing how to play it, the position of our sun relative to 14 pulsars, and the transition frequency of hydrogen atoms, serving as a universal cosmic clock. Everything was etched with the hope that if found by another intelligence, it could be decoded and understood without a shared language. For the mission scientists, the Golden Record was more than a romantic gesture. It was a statement of permanence that, even if Voyager's instruments fell silent, it would still carry a piece of humanity into the galaxy for billions of years. It might never be heard, it might never be found, but if it was, it would speak for all of us. What no one could have imagined was that decades later, far beyond the last planet, something out there might respond. By the time Voyager 1 crossed into interstellar space, it was already running on borrowed time. Its power came from 3 radioisotope thermoelectric generators, and with each year, the heat from their plutonium cores faded a little more. To keep the spacecraft alive, engineers at NASA's Jet Propulsion Laboratory began making hard choices, shutting down instruments one by one to conserve power for the systems that mattered most. The cameras had gone dark decades earlier after their planetary flybys ended, but other instruments continued to return valuable data. The magnetometer, cosmic ray detectors, and plasma wave sensors. Even so, the electrical budget was shrinking to the point where, within a few years, only the most essential components, the communication system, and perhaps a single instrument, could be kept running. Complicating matters was the sheer distance. At more than 23 billion kilometers from Earth, a single radio command took over 20 hours to arrive, and another 20 hours for a reply to return. Every adjustment, every test had to be planned days in advance. Repairs were impossible. Only careful reprogramming and creative use of aging hardware kept the spacecraft functional. Voyager 1 was still doing science, still sending back whispers from the edge of the sun's influence. But the margin for survival was thinner than ever, and in 2022, an unexpected failure threatened to end that mission far sooner than anyone had feared. In May 2022, the flow of data from Voyager 1 suddenly stopped making sense. The spacecraft was still sending signals back to Earth, but its telemetry, the vital information about its position, orientation, and health, had become scrambled, like a voice speaking in a language no one could understand. Even more puzzling, the scientific instruments continued to operate normally. The data wasn't corrupted in transit. Something inside Voyager had gone wrong. Engineers quickly traced the problem to the ACS, the Attitude, Articulation, and Control System, the part of the spacecraft that keeps its high-gain antenna locked on Earth. For reasons they couldn't explain, the ACS had started routing its status reports through a computer that hadn't worked in decades. The result was nonsense data reaching Earth, even though the system itself seemed to be functioning correctly. The real fear was that the antenna might drift off target, breaking the fragile communication link forever. With Voyager 1 so far away, there was no way to physically repair the system. Instead, engineers had to send a carefully crafted set of commands, knowing each one would take 20 hours to arrive and 20 hours for the response to return.